Hello, pre-calculus. I just left you guys, and we didn't have enough time to go through this 2.2 homework, so I'm making the video. We stopped at number 5. Remember how I said that direct variation, you need to have your constant always, your constant will always be in the numerator, but for direct variation, not only will your constant be in the numerator, so will what is being directly variated. So this is direct variation. Y varies directly as x. You always have your k here, but your x would also be multiplied by k. And if y varies inversely, so inverse variation, y varies inversely as x, that would be your constant of variation divided by x. So that's what we're going to use this thought process. So the current in an electrical current, I, is inversely proportional. So inversely proportional, I know that I'm going to have the situation where it's k divided by x, right? But to the resistance R, so this is like my x, with a constant variation v. So this is like my k. So this is my constant of variation divided by my r, because I is inversely proportional to r. So see, if it's I is inversely proportional to r, that's like saying y is inversely proportional to x. So look, my I goes where my y is, my r goes where my x is, and my constant of variation for this one is v. So now the weight of an object varies directly with its mass, and the constant of variation is g. So this time we'll be using the y equals kx thought process, because y varies directly with x, is y equals kx. This one, w, varies directly as m with your constant of variation g. This is going to be w equals gm. For number 7, the distance d traveled by an object falling for time t varies directly with the square of time, which is time squared, with a constant variation of 1/2 g. So my distance varies directly as time squared with a constant variation. There's my constant of variation, 1/2 g, and then it's varying directly with t squared, the square of time, giving us distance varies directly with the square of time with a constant of variation 1/2 g. The volume of a cone V is directly proportional, so that's directly proportional is another way to say directly inverse, right? Varies directly, so this means varies directly. So V varies directly to the square of its radius r and the height. Well, when it says and, it means multiply both of those. And so the constant of variation is 1/3 pi. So there's my k. My 1/3 pi is like my k. And then it's varying directly, so I'm going to multiply that by the square of r and h. So that means also multiply it by h. Okay, even though it says and, it doesn't mean addition. It means go ahead and multiply that r squared also by h, okay? So number 9, Boyle's gas law states that the volume V of an enclosed gas at a constant temperature varies inversely as the pressure P. So V, and I know P is going to go in the denominator because it varies inversely as the pressure. Now, I normally would put K up here unless it tells me a different one. Oh, no, it says constant of variation is K. So I'm able to put that constant of variation up in the numerator. That always stays in the numerator. And then when it's varying inversely, what V varies inversely with goes in the denominator. So volume varies inversely as pressure. Okay, so that gives me V equals K divided by P. Now we can move to problem number 10. Write a power function. State the power and the constant of variation. So this is the one where you want to start with y equals k times x to the a. And you're thinking, okay, well, I don't know what my k is, but I know that my y is 1 when my, my x is 2. So I don't know what my k is, I don't know what my a is, but I know my y is 1 when my x is 2. I also know that my y is 1/4, right? This is 1/4 when my x is 4. Okay? So those are two things that you know. Now you have two equations and two unknowns. And I can solve this by substitution. Okay, so we just have to decide what do we want to substitute. So I thought that if I solved this first one for k, I could just divide by 2 to the a on both sides. So my k is equal to 1 divided by 2 to the a. And then I could come over here to my second one and say 1/4, and then I would put in 1/2 to the a. And then look, this 4, I'm actually going to make 2 squared. So this is 2 squared to the a, and you can think of it like that, but you're still going to multiply 2 times a in the exponent, so it's going to be 2 to the 2a. And then I can say that 1/4 is equal to, I can say 1, and I'm going to bring this 2 to the 2a, or 2 to the a, up. So I've got times 2 to the 2a times 2 to the negative a. Got something on my screen, sorry. Okay, and so that leads me to 1/4, gosh, I'm running out of space here, it makes me mad. Okay, that leads me to 1/4 is equal to 1 times 2 to the a. Okay, which we don't need that 1, right? 1/4 is equal to 2 to the a. And then I think, oh gosh, this is actually 1/2 squared. And if I bring that 2 squared up, it'll be 2 to the negative 2. Ah, look at that. There's my a. My a is negative 2. So once I know that my a is negative 2, I can find k. 1/2 to the negative 2. That means I would bring it up, and k would be 4. So that leaves me for the answer for number 10. I know that my k is 4, and my x is negative 2. And so that will be your power function for this table. If I put any of these in, if I put 1 in, or if I put 2 in, I get 1. If I put 4 in, I get 1/4. If I put 6 in, that's going to give me 1/9. I think this point, 1, 1, 1, 1, 1 is 1/9. Let's put it in our calculator and make sure. 1 divided by 9. Yep, sure is. So all of these work now. So number 11, we're going to, start with the same thing. We got to remember y equals k times x to the a. And so I'm going to do the work over on this side. And so I've got negative 2 equals k times 1 to the a. Okay, sorry about that. So this one's kind of easy because you already now know that your k is negative 2. Because 1 to any power is 1, right? So you've got your k. And then you can use the next one, -4 equals, and now we can put that k in, times 4 to the a. And then we can solve for a here. So the first thing you want to do is divide by -2 because you want to isolate 4 to the a. So that will go away. This will be 2 equals 4 to the a. And so I'm going to make my 4 2 squared, just like we did before. So 2 to the 1 equals 2 to the 2a. That means 1 is 2a. So my a is 1/2. So now I got my k and I got my a. Here's my k, here's my a. And so this one's going to be y equals -2 times x to the 1/2. And that should be the function that would make all of these true. If I put a 1 in, I get -2. If I put a 4 in, I get -4. If I put a 9 in, I get -6. If I put a 6 in, the square root of 6, 6? I don't think that's supposed to be a 6. I think that's supposed to be a 16. If I put a 16 in, I get -8. Well, we just found a mistake on the homework that I didn't see until now. Oh my goodness, I better mark that maybe for next time we use it, if we ever use this homework again. I don't know that we will. Okay, but there's your two functions for 10 and 11. Now we go to number 12. A gas law states that the volume of an enclosed gas varies directly as the temperature and inversely as the pressure. Now this is interesting because your volume varies, so you always have your K. Directly as the temperature and inversely as the pressure. So the pressure had to go, the inverse variation goes in the denominator, the direct variation temperature goes in the numerator. So that's interesting that they did both, and that's okay because sometimes you see both. And then it's going to give us a scenario, okay? The pressure of a gas is 0.7 kilograms per square centimeter when the temperature is 294 kelvins and the volume is 7,400 cubic centimeters. Okay, so there's your situation. Then it's going to give you and we're going to use that to find K. Okay, we're going to be able to put these numbers in. We'll have V, T, and P, and we'll be able to solve for K. We're going to store it in our calculator. And then they're going to give us another situation. It says find the pressure. So once we find K, we'll be able to solve for the pressure over here when the temperature is 306 kelvins and the volume is 6,500 cubic centimeters. Okay, so let's go ahead and put our values in. 7,400 equals K times 294 over 0.7. And so if I was going to start solving for this, I would multiply both sides by 0.7 because I would want to get rid of my denominator. So, you know, that would get rid of that. And so that would give you your 0.7 times 7,400 is 5,180 equals 294K. And then, of course, you would divide by 294 on both sides. And that's going to give you your K. Now, I want you, it's going to be approximately 17.619. Okay, that's going to be the approximation. But I want you to store it in your calculator as K. Okay? And I wish I could show you this. I don't know how to show it to you with my iPad because I don't have a TI on my iPad. But I would put in 5180 divided by 294 and hit enter. I got 17.619,04762. I'm going to hit store and then I'm going to hit alpha and the open parenthesis, and that gives me K. Okay, and now it's in K. So now when I go back to do my, and by the way, I know in, if they want to solve for P, they would, your science department would have you start with this and solve for P. So what would you do? You would multiply both sides by P to get rid of the denominator. So if I multiply both sides by P, the P's cancel on that side, and I'm left with P times V equals K times T, and then I would divide by V. Okay, so now if I want to find the pressure for this problem, I'm gonna take my K that I stored, I'm gonna multiply it by that 306 right here, kelvins, because that's my T, and I'm gonna divide by my volume of 6,500, which they gave me right here, so I can solve for the P that goes with those two values. And so now in your calculator, you're gonna take 306 times alpha, open parenthesis, because that gives me K. I went ahead and hit enter, and then I put in divide by 6,500, which is whatever you want to do. I think it would have been fine if you put divide by 6,500 without hitting enter. I think you would have gotten the same answer. But I get a pressure of 0.829, and this would be kilograms per square centimeter. And so that is your answer for number 12. Number 13, it says Hooke's law for springs states that the distance a spring is stretched or compressed varies directly as the force on the spring. So we've got direct variation. It said varies directly as the force on the spring. So distance equals K times, I guess I better make force a capital F. I don't know what they do. So distance equals some constant variation times force. Because it was a direct variation, force stayed in the numerator. And then it gave us a situation where it says a force of 250 newtons. So when F is 250 newtons, the spring stretches a distance of 6 inches. And so that they gave us so that we could solve for K. So 6 is equal to K times 250. And so 6 divided by 250 is my K. And I can store that in my calculator. Or, well, let's see. It might be something where we don't need to store it because it might be, yeah, it's just 0.024. So my K is 0.024. It came out nice, so you don't need to store it. You can just say, okay, now my new equation is 0.024F. So that's your equation now, according to this scenario over here that they gave you, right? And so it says, how far will a force of 175 newtons stretch the spring? So we're looking for the distance it would stretch if the force was 175 newtons. So we're going to take the 0.024 and multiply it by 175. And that gives us a distance of 4.2 inches. So this is your answer. Okay, so the diameter of the largest particle that can be moved by a stream varies approximately directly. So varies directly as the square of the velocity of the stream. So the diameter of the largest particle that can be moved, you've got some constant of variation varying directly as the square of the velocity. So I read that and I write this. Diameter varies directly as square of velocity. That means it's equal to some constant of variation times the square of velocity. So a stream with velocity, here we go. It's given us a situation where we can solve for our k. A stream with velocity 0.5 miles per hour can move coarse particles about a distance of 0.1 inches in diameter. Okay? So find the velocity. So now they want us to solve for another velocity. We're going to use that to solve for k, right? We'll use this right here to solve for k. They then want us to use that k to find the velocity needed to carry it a diameter of 0.25 inches. Okay? So let's find k. So 0.1 equals k times 0.5 squared. So I'm going to take 0.1, divide it by 0.5 squared, and that's going to give me my k. And if you put that in your calculator, you're going to see that your k is 0.4. And so now you can rewrite it with your k. There's your equation. That's your main equation, relationship. And you're going to use this 0.4 times v squared to solve for v, okay? Because we want to know, well, what if the diameter is 0.25? So the first thing you would do is divide by your 0.4 to isolate your v squared. And then you're going to square root both sides. And that's approximately 0.791. This would be miles per hour. So this is the velocity needed to move those particles 0.25 inch in diameter. Okay, I hope that helps. I hope you got the answers right. I hope you were able to do some of it